Okay, everybody, welcome. We're about to start. We're starting. This afternoon, the keynote lecture is celebrating the work of Morphogenesis, one of the largest and most creative architectural practices of India, but also, I would say, of the world. A practice that was co-founded by Manit and Sonali Rastogi, both of them graduates of the AA. Manit, it's a pleasure to welcome you back to the AA after these years. It would have been great to have you here in physical person. We'll do it, but at least we have you in digital presence, and we look forward. I'm especially interested to see what you have been bringing under your copyrighted design process. So sustainable, optimized, unique, and livable. Ladies and gentlemen, Manit Rastogi.
Thank you, Simo. It's great to be. It's great to be on the same platform with you. It's been a long time, but it's been an incredible time, and it's just ironic that when the world is seeing one of its worst acts of pandemics, at least for in my lifetime, it's when we share this opportunity, and I think this is where sustainability, sustainable design, resilience has shown that it is why it is so important for this world to take it in its mainstream and to be really concerned about how we think about our future and what has happened in the last 9 months or a year. So thank you, Simos. And for those of you who don't know, I was a student at the AA. I studied under Simos, and Simos is sort of, I guess he's the godfather of sustainable design. He's sort of done this for a long time. So it gives me great pleasure to show some of the work of our firm. A lot of it is, of course, heavily influenced by that thinking and that time that I spent in England and at the A. So without much ado, I'll get straight into my presentation. Let me see if I can do this. Okay. Right. So as Simos mentioned, my presentation today is about building resilience. And till about a year back, we used to call it building sustainability. And I think we sort of looked at not changing sustainability, but increasing the scope of sustainability to encompass many other factors which we used to think about, but didn't sort of analyze with the rigor that we were analyzing our buildings in terms of sustainable design. So, when I came back from the A, this was about now 25 years, and nothing really. India is one of the largest populations in the world, next to China. It's about 1.4 billion people, but urban India has all the sort of issues that large emerging nations have. It has water issues in our cities. Our cities are running short of water, but I think that's not only an Indian scenario now, that will be a global scenario. Climate change has affected India tremendously. We've had some of the worst weather patterns in the last year or so. We've had issues with energy. We've had issues with pollution. And some of this led to a lot of our early thinking why we would pursue the whole sort of genre of sustainable design and see if architecture, if buildings, the whole built environment can help resolve what our politicians and what our cities over the years have not been able to do. So very early on, we sort of looked at what's really the issue with energy. And we did this study about a couple of decades back. At that time, India's population was 1.2 billion, and now it's about 1.4 billion. And just very broadly speaking, in terms of the fact that India has a daily solar radiation, which is on an average 5.5 kilowatt hours per square meter of the country's mass, we only really need 0.003% of this land mass if we were to just drive our entire energy by solar. It's actually nothing. It's only 2% of the wasteland, the deserts of India, is all that we would need to drive all the energy, not for today's requirement, for what is projected for 2050. And we started thinking about the fact that what really is the issue then? Why? And then the second part was water. And if you just look at the annual rainfall, I know this is very macro level data, but it laid the context of what we would do at a micro level, given the fact that energy wasn't a problem, but it is. Water isn't a problem. 2% of the rainfall in India, if harvested, would suffice 150 liters a person, for 1.4 billion people. And so what are we really doing? And we were sort of, looking at our cities, and we were looking at our buildings, and we had developed this sort of system where our buildings would consume energy and they would consume water and they would generate waste, and it was a one-way flow. And we began thinking of how we can short circuit that. How can we begin to look at our architecture where it can go off grid? If we were to assume there was no energy and there was no water, how can we begin to go and design architecture that would allow us to do that? And then this came along, and this was now last year, the world's largest mass migration. 139 million, 140 million migrant workers were displaced in this pandemic because India is largely a country where migration is critical. And these images drove us crazy. The world hasn't seen something like this before. And most of these people most of these migrants are essentially people working on mine sites. A lot of them are construction workers. A lot of them are working in industries, are working in buildings, are working to service urban India. And that's when we began to think also about the fact that we need to expand the scope of sustainability or sustainable environmental design as we understood it for the last 25 years, to begin to affect all the stakeholders, not only the building, because in a sense, we can save the planet by saving the energy, but that's not the problem. The problem really is the people. And how do we begin to bring sustainability and hence resilience to a much larger population, all the stakeholders involved in the building process? And we began to map out, and this was early last year, all the hotspots of migration. So my presentation today is going to sort of overlap in two parts. One part, of course, is going to be what we think about in terms of sustainability and how we tackle that. But second also is how we over the last several years have begun to engage with communities, with the people who are actually building our buildings, and what we think about that and what architecture can do to a nation in terms of providing models of design. So, one of the projects I'll show you towards the end is for decentralized industries where they can operate even in the hills, in remote areas without where there's no grid or there's no access to water. So what I have mapped out here are essentially 6 projects. The first one I'll present to you is in Jaipur. It's one of the first projects that we did after we came back from England. It's a desert climate. Second one I'll present to you is in Delhi. It's a composite climate. Third one is in the hills, a very remote area called Rishikesh in Uttarakhand, where there's virtually no infrastructure. Kolkata, warm, humid, coastal climate, in fact, very humid climate, moving across to a city called Surat in Gujarat, which is a very arid climate, a lot of glare, a lot of diffuse radiation, and then on to Hyderabad. I mean, these are essentially, so India is generally perceived to be one country. It's not. It's more like the Indian Union in terms of culture. It's as disparate as it gets. If you look at all the climatic zones that exist anywhere in the world, are sort of encapsulated in this one nation with 1.5 billion people. So moving on, what Simos was referring to, the only reason we copyrighted our design process, which we developed over the last 2.5 decades, was more for our internal yardstick, so that and in fact I was a director at the School of Architecture for 5 years, and Indians, by and large, like very, very tangible data. So they like metrics, evidence-based design, and a lot of that also comes from a long history of very limited resources. So no one, so even if you have a client here, and you tell them my building will be sustainable, they don't understand until you tell them why. So what you see on the top here is through this process of sustainability, where our main aim has been to push our projects to net zero energy, net zero water, fresh water, and net zero waste to landfill. Optimization has been mostly about how do you build less, how do you do a lot more with a lot less. And typically speaking, a typical RCC building weighs 1,500 kgs per square meter. And if one person in an office building occupies 10 square meters, that's about 15 tons of material traveling to provide shelter to one person in an office. And if you take a residence, it's much higher. And our argument has been, therefore, that the lesser you build, the more sustainable you are. So optimization is a strategy and a set of metrics that we have developed where we try and build less. And essentially, that's about removing embodied energy, and that's about reducing CO2 emissions from how you build something. Uniqueness is about, again, a set of metrics which looks at tradition, heritage, and culture. And that third philosophy and third arm grows from the fact that across India, given the fact that price points of construction are extremely frugal, everything started looking the same. It didn't matter whether you were in a cold climate, in a temperate climate, in a hot climate, in a warm, humid climate. But by and large, most buildings and everything started looking the same. And that's because they were adopting processes of construction and design that allowed for that to happen. And we found ways of digging into the past to find ways to build the future. And that's where we sort of got the unique. And livability was essentially about engaging not only the client and the end user of our buildings, but trying to engage the people who built that building, the communities, the local craft, the local craftsmen, and see how we can sort of build that relationship. Because architecture can have wide-ranging effects. I mean, typically speaking, there are about 400 sub-industries attached to the building industry. And if you begin to think about it as a far larger ecosystem, then it's not really about that one building that we built that has great performance and energy. It's actually about 400 other sub-industries and thousands of people that get affected. So we've been tracking our metrics for the last 2.5 decades of practice. And all the projects that we've built, we have got about 560,000 people who either live or work or study or play or shop in them. We've built about 50 million square feet. That's about 5 million square meters. Now, when we talk about energy saved, CO2 emission, and fresh water, this is all benchmarked to the ECBC, the Energy Conservation Building Code of India, which is like a green building standard. And based on those standards, all our buildings are under post-occupancy evaluation. And we keep a track of those numbers, of what these buildings are achieving today. But that's over 2.5 decades. So I'll start with the first project. And this project dates back about nearly a decade or so. It's called the Pearl Academy. It sits in Jaipur. Jaipur is in Rajasthan, and it sits in a desert climate. There were many challenges to this project. The first, of course, was the fact that cost. Now, I'm sure a lot of people here don't know, may not be familiar with cost of construction, but this project was built at $200 a square meter with all interiors and all the energy infrastructure, everything all told, which was virtually impossible in that time. And of course, a climate like Jaipur, which goes up to 48, 49 degrees Celsius in the summer, but can drop to close to zero in the nights in winter. And we began thinking about how we are sort of going to be able to build this building. And the first thing that came to our head was to throw out the air conditioning. because you throw out the air conditioning. Along with that, you reduce all the electrical equipment, but no more so, you reduce the fact that the power generation is also done locally. So you have these diesel generating sets that generate that power, and you get rid of that as well. And we studied a lot of the traditional architecture. We used computational models to understand how do step wells work, why are they cooler in at the bottom than the top. We understood evaporative cooling, jalis, ventilation, shading, and we then studied the local geology. A lot of this, I may repeat, was being driven by the fact that if this building had to be built at that cost, then what could we do? So we mapped out a 200-kilometer radius. We said every material that we will use will come from that, because transportation costs are extremely heavy. And the other thing that we discovered at the time, which sort of I think emanated also a bit from my studies with CMOS, was that the temperature of the Earth about 3 meters below the surface is equal to the average temperature of the region. And in Jaipur, like I said, which goes from 0 to 48, 49 degrees, the average was sort of floating around 25. And we said, hey, that's a very useful, and which is why the step wells, if anyone has visited India and they go to the step well and you come down, it naturally feels cooler because the earth banking along with evaporative cooling is a phenomenal cooling mechanism. It's an underground air conditioner, naturally driven. So we said, fine. Now, typically speaking, any institutional building in India would be built as a block, and then you would sort of have the open space, which is the recreation space. But when you're in a desert climate, that open space is really worth nothing. And a key example of that would be Dubai. I mean, I know that we must have a whole team there. And these large outdoor spaces become mostly unusable through the year. And we said, well, we won't do our building vertically. We'll spread our building out and use the whole building as a shade, like a tree. And therefore, the space under the building will become viable. We did a very optimized, simple rectangular form. Idea was again to decrease the amount of surface area that we exposed to getting heat gain. And we went through a series of courtyard morphologies. The idea really being to keep the sun out, but let the daylight in. I'm not going to show you these diagrams. All of you probably know them very, very well. But the idea really was to develop, and because it was a design and fashion school, the emotional element was that if you were inside this sort of very rigid form, which was driven by our environmental criteria, in any courtyard, the courtyard should not be sort of like a rectangle and it flows. It should sort of flow freely like a Mobius strip. And that was sort of the model when we began over about a decade back. To achieve the parameters of, without air conditioning in a desert climate, we sunk down 3 meters. We recycle all the rainwater and we recycle water from the toilets by filtering and using a treatment plant. And we created our own step well, Bauli, in effect, which allowed for evaporation through the courtyards and cooling the building internally. And that sort of negative space, if I may, was pulled out of the program. So we were supposed to build about 25,000 square meters. We did. We built about 2/3 of that. And that entire area underneath, which to date operates at about 28, 29 degrees Celsius naturally, is used for an outdoor cafeteria, is used for various functions, performances, etc. And that whole underbelly section was designed to do that. These are just some of the pictures of that sort of step well that we created. All the water is harvested. Not a single drop of water leaves the site. But we were just trying to do, just work with limited resources effectively. And obviously, the whole thing sits in shade. It captures the wind flows and it cools the building down. We looked at insulation. Insulation was very critical for a project like this in a desert climate. And there was a local community that made pots. We couldn't afford the sort of very expensive 50 mil glass wool or rock wool insulation. And we thought that pots, which were used traditionally, would make for great insulation, but air is a great insulator. And we use these inverted pots with a layer of screed on the top, and we use that for insulation. The pots were made on site by this local potter community. For the external skin, we kept our window-to-wall ratios very, very optimized. We are at about I think 20 or 25%, providing adequate daylight. And we created this buffer space, which is essentially a service space and a screen. And the screen is made from, again, a set of local community who make cement concrete jalis on a very simple system. And we ran all our services on the outside. So the screen allowed for the fact that the entire windows go blinds free, and the design of the screen changes based on the orientation. And all the services are openly accessible. The sprinklers run here. We use the sprinklers as a facade cleaning system, because once a month they are supposed to test and flush it. So that sort of cleans that up. And that's the building when it was finished about a decade back. So all the materials are still on everything here was from within a 200-kilometer radius. We did achieve the price point. And this building went on to become very popular with various schools of architecture. They've gone and studied it. We've had students from various programs in masters programs studying sustainable design, recording temperatures and seeing it. And for the last decade or so, it is sort of consistently in the summers, when external temperatures have hit 47, it's hit 29 degrees inside without air conditioning. It runs on an energy performance index of about 25 to date. Very simply, we get the bill that just divided out. And whilst it was being built, it gave a certain level of employment to the local community. And that gave us a lot of inspiration. And we thought that, if it was possible to get an 18 degrees delta by passive design, and it was possible to create something in these sort of kind of price points pushed by the adversity of price, then what is it that we could do as we moved on? And that's when we started sort of putting more formal metrics. And which is why I'll jump to a very different kind of building, which is the British School, which is in Delhi. That's a composite climate. And here, budget was not an issue. And our brief was, to begin with, because it was the British School, was that they wanted it to be centrally air conditioned. All British schools pretty much across the world are either centrally heated or centrally air conditioned. And we argued the fact that if we can begin to achieve as much as we can naturally, then we will do so. And this project is about, I think, 6 or 7 years ago. And we then spoke to the clients, which was essentially the High Commissioner and the board, and we said that why don't we look at this 5-acre site and generate try and do India's first net zero energy, net zero water, net zero landfill, waste to landfill kind of building. And I said, fine, let's give it a shot. And so we did the math on the water, and from the 5 acres of land that we had, I'm not going to go through the calculations, but we could support a population of about 1,300 students. And we said, we'll do this in reverse. We said, so the notion of carrying capacity comes from the fact that what the land can afford in terms of water and energy is all that we will build. And 1,300 students worked very well for them. Now the problem with a city like Delhi is all our rain is concentrated in 3 months. So you can't store that much water for the rest of the year. So what you do is you dig down and you find an aquifer that's pure, and you use that as an underground tank, and you use that as an exchange. So you put water back into it and you pull it out of it. And over the year, you go net zero on water for 1,300 people. We took the same 1,300 people, and then we went about building out how much, because we needed to build about 20,000 square meters for fitting out an IB school. And we were trying to work out what is the correct ratio of rooftop solar to number of levels that we would need to be able to get to net zero, and therefore what would be the target EPI that we need to achieve. And after a lot of to and fro, we came to a 4-story building with a target energy performance index of 56 kilowatt hours per square meter a year. Now that number would by necessity drive a lot of passive design, where a lot of the heat loads and a lot of the lighting loads would need to disappear. And that's when we would be able to be net zero on water, net zero on energy. And again, we looked at a lot of, in Delhi, there's a very old city called Shahjahanabad. We looked at how those morphologies work, how some of the earth banking worked. The other also key area was safety and security. And because we were propagating the idea of having open corridors and we were not doubly loaded and had the air condition, the issue of security, CCTV cameras, and we came up with this idea. We didn't come up. We studied this idea of eyes everywhere. And if you look at any old vernacular evolution of any city anywhere in the world, where there was, in those days when there was no police several hundred years back or CCTV cameras, the cities were designed in a way that there were eyes everywhere. And that really was a security. So a combination of the two factors, we began to look at morphologies where we would be able to get eyes everywhere, step terraces, shaded courts, and we sort of landed up with this sort of model with a rooftop area sufficient to make this into a net zero energy project. Some other small things that we did, we put the labs on the top because the labs are constantly mechanically ventilated because of the fumes, and that automatically creates a buffer for everything underneath. We created natural voids for the wind flows to allow for the courtyards to function properly. And because of the orientation of the site, where we had pushed that form again from like we done earlier, we began to look at the Jali formation. Most of our teaching areas were on the northeast and the northwest, while the southwest was essentially a large screen just shading out the courtyards. A lot of this was built on site, so we came up with this sort of construction methodology of again full windows and having a secondary screen. The screen, of course, varies its opacity and density based on what's behind it and what orientation it works to. And yes, and that's sort of now the completed building. We did a lot of modeling for. So we had the classroom, and that was built, that was done perfectly. But to us, what was more important was to be able to create enough open spaces within which would be comfortable through the year. And we were targeting a delta of about 8 to 10 degrees in perceptible temperature in the outdoor areas in the school as compared to the external temperature. And then here's that project. So that's the front screen that shades off the southwest and sort of creates a full microclimate behind. Again, open corridors. What you see here are air filters because it was a British school. We didn't air condition the entire school, but we did for the classrooms we did, and then create these sort of passive spaces. A lot of outdoor spaces. Now, well, this is a bit old, but the trees are grown now. Yeah, and that's the school. Now, on our post-occupancy, we to date have an EPI of 52. It's the only school in India right now which got a GREHA 5-star rating. GREHA is India's own green rating system. And as I am a founding member of the green rating system for, I can say that I had, it is genuine. I didn't falsify any data, but it's operating at a 52. Now, what you see here is a combination of surface temperature and air temperature. So, and then we sort of map that back to perceptible temperature. So at a 44 outside, we did manage to get a 10 to 12 degree delta in all the open spaces inside that school. So to date, and we keep our classrooms at about 26 to 28 degrees. So there is a gradation as one steps out and moves through this entire project. And it operates today as a net zero on all accounts. So that was in that sort of composite sort of climate. I mean, like in a composite climate, the winters aren't a problem. The real problems are, and it's not even the summer because shade, thermal mass, screens, a bit of evaporative cooling, that works. The real problem has always been the monsoon. Why it works really well in schools is that Indian schools are shut in the monsoons. That's the holiday period. And that sort of works really, really well, which doesn't in other kinds of typologies like offices or residential and which sort of brings me to this third one. This is a campus. It's a 100-acre campus for a very large technology ID firm called Wipro. They're amongst the three largest listed companies in India. And they do these sort of really massive campuses, have tens of thousands of people working there. This is located in Hyderabad, in Telangana. It's a very strange sort of climate. It's not very adverse, but it's got a tremendous amount of diffuse radiation. It barely has no cloud cover, pretty much through the year, and temperatures do go up, but it's not that high. And it has reasonable wind speeds, reasonable wind temperatures, but the glare is just incredibly high. The diffuse radiation is what pushes temperatures up. And we worked on this project with S.O.U.L. It's one of the several we've done with them. And this is where we began. So we looked at the site, and that's about 100 acres. It's divided into 3 zones. And that zone 2, as we discovered, was largely unbuildable because it sat in a radius from a lake which wasn't too far away. And even as we discovered, it's sort of a bit low-lying. And the really buildable areas were these 2. We again pursued the idea of a carrying capacity. We had the 100 acres, and we worked out backwards as to how many people can we support from the rainfall. And we then, to store that water, because, like I said, Hyderabad is very strange in the sense that its entire geology is slate rock. So it was very hard to get to an aquifer and do water exchange with. So we really had to build a reservoir. So at a 4-meter depth, we needed about 15 acres of water reservoir to support 15,000 people working there. And again, similarly with energy, we worked out that if we hit a 60 EPI, then we will be able to, with 15 acres of a solar farm, which we have planned over and above the water reservoir. So essentially, the solar farm shades the water from evaporation and picks up the energy. We will be net zero on both accounts. And that's what we really did. So we identified the low-lying area. Everything slopes there. We get the natural rainwater. It's a 15-acre lake, about 4 meters deep. And then it's sort of got the solar panels that sit on top of it and on the site and shade it. And that piece of the land will never get overshadowed. So we could do the solar farm, 15 acres, on the site itself. And that sort of set up the basis of the first series of master plan. The second exercise was, as I'll just go back, was how do we begin to hit a 60 kilowatt hours per square meter per year, of which 25 is on primary energy, which is lighting and air conditioning or ventilation, and the 35 is on equipment. And how do we begin to get our building to work with the 25? The 35 was a given, so that's all internal equipment. The question really was, how do we work to 100% daylighting on the floor plate, and how do we bring our air conditioning requirements down to a point where through the year, and to remind you, these buildings tend to operate about 10 to 12 hours a day, 365 days a year, because they're essentially very large tech companies. So we began this exercise where we did about 8 of them. We did many more, but we sort of isolated 8 morphologies which were built upon isolated single towers, a series of square towers, courtyards, a hybrid of the tower and the courtyard, mid-rise high density, low-rise high density, micro courtyards, and we came up with several morphologies heuristically, and then we began to test them. So various kinds of ground coverages, various heights, and we then put them through a series of analysis. So the first analysis that we did was, of course, for wind, because wind was critical for us to, if we were to hit that 60 EPI, which is 25, we also needed to be able to get a lot of the functions from inside the building out. And a lot of the functions to run passively without air conditioning. Of course, where the essential work was happening would be air conditioned for various reasons of, the data centers, they need very tight control on air conditioning, etc. But how much of this could be and for that we needed the wind. Now, predominantly Hyderabad had an east-west wind, and we put all these various forms. We selected 5 that performed reasonably well. We then put them through the horizontal plane. We were trying to look at what, in terms of seasonal solar radiation, would the insolation be on the lower planes, and basis that we picked up a certain scheme. We then looked at daylight autonomy, for each of these 8 or 9 different schemes, and then again began to identify. And this was a highly iterative exercise between wind, solar radiation in the open spaces, and daylighting within the internal spaces, and what morphology would suit it the best. And finally, we selected the option which was sort of the micro courtyard option. And after doing a series of CFD runs on it, we cleaned up the entire the model. Again, this was highly iterative. And if anyone is very good with algorithms, this is a great one for that kind of process. And then we sort of finally ended up. So the first phase is what is now under construction, which I'll take you through. And then we've already done the urban design for the remaining 3, so that in a sense, the wind flows, the evaporative cooling, the shading, all those parameters remain the same. Coming to that first phase, which is approximately about 1 million square feet, about 100,000 square meters. We began looking at the outdoor spaces and trying to push the agenda of how can these outdoor spaces really begin to take primary functions. Can they replace the meeting room? Can they replace the gym? Can they replace the food court? Can they replace, what functions can they actually physically replace outside? And we went through a series of analysis, looking at a combination of having no roof, no fans, no dry misting, and having only a roof, like a lightweight tensile roof, a combination of roofs and fans, plus dry misting. And we then did a cross analysis of the fact that what would be the financial savings vis-a-vis these spaces sat inside air-conditioned spaces. And that sort of led to this design, which I call a large desert cooler, very traditional large, desert cooler is essentially what used to be there before air conditioners, a box with a fan, and you had these this sort of hay on the side where water ran down, cooled it and shoved it through. And so the entire plane, which sort of sits on an elevated podium, was designed for those wind flows and those outdoor spaces. And we worked with SBP. We got this sort of height with this sort of tensile roof in combination with Transolar and us, and we sort of got this entire outdoor space working in a way that it is comfortable through the year. So it's comfortable for rain, it's comfortable for the summer, it's comfortable for the winter. And by and large, this entire outdoor space now takes on primary functions. I won't spend too much time on the indoor spaces. We went through a similar exercise of looking at various kinds of mechanisms of how can we remove as much air conditioning from the inside, whether it's underfloor, with heat recovery, hybrids, low velocity fans, and came to an optimal solution. Again, a lot of this is very cost-based, but it's also but it's a combination of sustainability and cost. And of course, settling for the fact that our client agreed to an internal temperature of 28 degrees, which is very useful because, and it's actually correct, because external temperatures can go up to 38 to 40 degrees, and working out the whole system based around that. So when the project, when we finished the design, 56% of the area was in under air-conditioned space, but consuming about less than half the air conditioning. So typically speaking, in this region, a building would consume 250 square foot for 1 ton of air conditioning. This project is operating at about 650 square feet per 1 ton of air conditioning. So even though 56% of the spaces are air conditioned, they're consuming less than half. About 35% have been moved to natural ventilation. Now, when I say natural ventilation, and I say the third piece, which is shaded outdoor, all of these are achieving thermal comfort conditions through the year. Greater than 90% of thermal conditions through the year. So not only did we manage to get about 10% of that area outside, which is about nearly 10,000 square meters. So cafeteria, gym, recreation, library is in that outdoor shaded space that I was showing you. We have outdoor meeting rooms, which were removed from the inside area, and of course the rival plaza. And in the naturally vented spaces, we have various other functions. So effectively, only half the building is air conditioning. This typically would be at 100%. And anyways, this is just some of the views of the building. And that's the building currently under construction. It got slowed down last year because of COVID. That's the sort of east-west axis for the wind, and the columns have these water channels that drop down, causing the evaporative cooling across the winds that go across. The central courtyard, which is shaded, which now will contain, and that'll sort of have the tensile roof with the food court, the gym, the library. And even at this scale, I mean, a grade A office building, operating at a net zero on all three accounts. But more importantly, was the fact that we could do this. We could break that, mindset that office buildings can actually, at this level of density, there are 15,000 people who are going to work here by the end of this year. And of course, I won't get into the details and the metrics, but we broke a lot of ground here. I mean, of course, between our envelope design, our energy performance, we are at about 35, under 35. We wanted to be at 25. We didn't hit 25, but we're at about 30 right now. And fresh water demand, we are at under 50% of that. We went to the point that where even the structural design was defined in terms of how much steel and how much concrete is going in and how can we optimize to save CO2 emissions in embodied energy. But it did work, and it's about to get completed. So anyways, post-occupancy will tell us, but that's where we were. I'm going to shoot across. I'll just do another, I might probably be out of time already. I don't know how much time do I have left? Do I have 10, 15 minutes?
Yes, of course.
Okay, so dramatically different project. I mean, this sits in Kolkata, which is the extreme sort of the extreme east of India. It's got a warm, humid climate, extremely humid, and temperatures don't change very much through the year. It's very close to the sea, but it's also in some senses, the cradle of civilization. A lot of the first universities, the first art, knowledge, culture, music, a lot of that was born in this part of the world, in this city particularly, and we began looking at the site. Now I think the total area here is about 3 million square feet, if I'm not wrong. Yeah, about 300,000 square meters, and it's a 17-acre site. Now, we did the math on this. We couldn't push this one to a net zero because, like I mentioned earlier, any environment that is high humid, the city maintains a greater than 70% humidity pretty much through the year. And therefore, in a mixed-use environment consisting of offices, hotel, conferencing, data centers, etc., the air conditioning was inevitable. However, what we started thinking about was what could we do in terms of the entire site, and therefore we set up a site plan where we could maximize the wind flows through the site, and all the buildings. What we did here was because Calcutta sits on a 22 degrees latitude, which is pretty much the tropics, but we tilted the buildings 22 degrees to pure north, and what that allowed us to do was essentially shade from one side. Because when the sun overshoots, you end up shading from two sides, and it led to a 25% reduction in solar exposure. We found this this very interesting. But every time you tilt a building towards the east from pure north, by the latitude the building sits at, it actually helps cut down It helps cut down solar exposure naturally, which helped reduce the amount of shading we had to put into the building in the first place. Then once we sort of had that sort of east-west axis, and we left a lot of cross axes as well, because we wanted a lot of natural ventilation. Wind speeds are not very high in Calcutta. They're at about 2.5 meters per second, but over the year, they changed direction. And which is why we sort of had to have this sort of thing sort of very free and as opposed to the previous one that I showed you, which was very fort-like, but very channeled. This had to be sort of very open and transparent. I won't go to the landscape design of how that sort of works with the wind flows. The second problem that we had was a lot of this was very large flow plates, 40, 50,000 square feet flow plates. And by and large, what happened to large flow plates traditionally in these kind of is that you get these sort of very deep 60 by 60 or 50 by 75 meter deep flow plates, and your daylighting drops to on a CDA or if you're doing daylight autonomy, or it drops to anywhere between 40 to 50%. And we took the same area and we changed the morphology of the building so that we could push that back to about 90 to 100%. And I mean, the point really about that is the fact that you don't really have to work with the form, which is a given. But if you go iterative, the same exercise allowed us to break this up into where we put our core and how the form sort of breaks up where we get 100% natural daylighting. So that was sort of the final piece of design when we finished up, I think, about 2.5, 3 years back. It's been in construction ever since. So we then began to look at the fact that now that we had a microclimate on the site, as you can see, this all reasonably well shaded, it's well ventilated. We now started working with a lot of the local craftsmen. And that sort of goes to my earlier point about, how do we work with local communities? And we found a lot of this sort of tradition, art, knowledge, culture, and we brought that back. So, hello?
We're here.
Okay. I think I would hear something. Okay.
En Albacete 13 bajo cero, en Toledo, recuerden que en Teruel y también en Toledo han sido temperaturas las capitales de provincia, vean esos 25.
Okay, great. Yeah, so we treated the entire 17 acres of the site as an open air sculpture and art gallery. Naturally ventilated, naturally water protected, 17 acres of outdoor, if I may, an arts and crafts museum. We worked with a lot of the local art schools and the local craftsmen who had this incredible craft who make all these sort of sculptures. And we then used a lot of the traditions of Bengal, of Calcutta, and abstracted them into this sort of graphic artwork, which the artisans could work with. And we then started using the west and the east facades, because all our buildings were north-south, albeit turned 22 degrees. And started working with them into sort of creating this urban art form, where it provided great amounts of insulation because they were just carving local stone, and we were working with that. And of course, working with the local alphabet, and again working with the stone, and coming up with this sort of 500 meter by about 100 meter long urban art facade. This is all west, and a lot of this sort of being crafted by local craftsmen. And again, on the other side, on the east as well. So that's the project, again, under construction, where a lot of this, again, is being done on site. And this we've done sort of as a very, very deliberate move in terms of trying to, these are dying communities. Craft communities are dying communities. And I think the more we work with them, the more we learn from them. They seem to have a better heuristic understanding of what we understand computationally. And this entire sort of 500 meter by 100 meter high urban facade is being put up by these local craftsmen, and eventually sort of leading to that on completion. So we managed to get in a very, very humid environment. We got an EPI of 43 by a lot of these measures. So we are 90% daylit, zero glare, which is critical because what you really don't want to do is draw the blinds if you get the glare and then switch the lights on and it all goes south. So glare-free, 90% daylit, window-to-wall ratio at 25%. Our facade is at 1 watt per square foot, envelope load design. And of course, the entire site is fully ventilated. Then that's how we sort of managed to hit the 43 degrees. And even in a humid environment, we've got a 5-degree delta in perceptible temperature. So at a 36 degrees to a 31 with ventilation, it works really well, even when you go and stand there on the site even today. And I think I'm going to sort of, in the interest of time, I'm going to do this last one. It's a precious project. We finished this, and it's precious because it was done during the COVID times. It just finished recently, a few months back. And this was a project that came to us about a year and a half back, pre-COVID. And it sits in a remote area in the hills in Uttarakhand. I'm just very quickly going to go to a picture. That's the site. There is no power cable. There are no drains. There is no water. There's water, but there's no water supply and a lot of the community that lives here actually makes this product. Now, Forest Essential is a luxury global brand. It's an Ayurveda brand of beauty product. And a lot of that is, and a lot of the people who make that product live here, and they walk or they travel about 20, 30, 40 kilometers to the town below to work there. And when the client came to us to redo that factory, and we said, why don't we build something here where they live, where they can work? And they said, but no infra. And our site is actually down there. And this is sort of very broken road. And we didn't even have a road leading to where they had the piece of land. And we went there and pre-COVID, and we looked at the community, we looked at all the local materials, we looked at how they live, and we found a very high level of resilience. And in that 1 kilometer radius from that site, we found about 800 people. There were about 150 hutments. And we said, fine, we're going to build this here. And we had a great client who agreed. And of course, it had to be completely off-grid. But also because we didn't want to get no material could come here. There was no road bringing trucks of material up here. So we built with very, very simple form. A lot of it was driven by what local materials we had. Courtyard, south-facing for the solar panels, and then a secondary terrace for drying some of the Ayurveda stuff. Naturally ventilated, all driven, good passive principles of design. Nothing very, very innovative, but easily buildable. Of course, we did a lot of studies pushing down the window-to-wall ratios. Glass was the one material that we had to get from a remote town. And we went through a series of exercises from the base case, which was the vernacular, and the fact that we were going to put a production factory making these Ayurveda luxury products that exported to New York and London and Paris, and are in shops on the high street. And essentially, that was a sort of finished section where, because of course it gets very cold in the winters, it's high in the hills, it's warm in the summer, and we sort of managed to get through the year a reasonable level of humidity and temperature control purely passively. More importantly, it was entirely built by the people who work here, by the community of people, and the architecture and the materials were all based around that. We learned a lot more about passive design from them, of how to handle this in winters and summers, how to harvest the water, reuse the water. And that's sort of the project, sort of sitting sort of off-grid, isolated. Of course, it's net zero, it's energy positive now, but and it's energy positive and supplies some power to some of the hutments as well. That's the factory now in use. Low velocity fans, windows open, natural daylight. There's a community that's a project by the community, for the community, built by them, supplying a product to the global world. And that's setting up there. It's used as a school in the evening by the same community. And and that's it. Yeah, so I'll skip the last one. I think, I think that's sort of my hour coming close to being nearly up. And this is just sort of a two-decade history of a variety of projects across various climates and various challenges. But at the core of it has always been the same principle. We begin by thinking, what if there is no energy and water? What do we do? How do we build? And of course, you will consume. So get as much equipment out of the building. Get rid of the air conditioning as much as you can. Reduce your heat loads. Work as much as you can with local materials with the local communities. And that's what will get character and identity, and hopefully will lead to an architecture of resilience. So that's it. Thank you very much. That's my presentation for today.
Thank you so much, Manit. Thank you. Thank you for this fascinating overview of the journey that morphogenesis has taken in these 25 or so years. Thank you for sharing it with us. I was just thinking as you started presenting that building that I've known a little bit, the Pearl Academy, and I knew a little bit about it because one of our students, as you know, we have many students from India. One of our Indian students was taking it as a starting point in the same way that perhaps you were taking the vernacular model. So that it seemed to me that now your projects are becoming the new inspirational model, the new vernacular, so to speak, for younger architects. I don't know how you feel about it, or whether it is actually happening or not. I do hope that you have a few more minutes. I will invite the audience for questions in a minute. But I wanted to say, firstly, myself, that I think this has been an amazing journey, very productive, but also very effective at the same time. Of course, there is this multidisciplinarity in the projects, and I wanted to ask you, how do you deal with the various demands that each of these projects makes? Do you have all the specialties, all the skills in the office, or is there collaboration, like I saw the name of Transolar there, in relation to climate analysis or whatever? So how do you do this, and how do you keep in touch with the projects after they have been inhabited? I mean, is this some sort of post-occupancy study? Would you care to comment on
Yes.
that?
Yes, Ivas. It's a very good question. So there are two parts to this. The first part is that architectural fees in India are very stretched, and you normally cannot afford high quality consultants, like say a Transolar, to come and work with you. But however, so we have developed in-house competency. We have developed our own tools. Now it is not, and because of the experience, it's not necessary that we have to put every project through exactly the same level of analysis, because a lot of it also carries forward in terms of knowledge and wisdom. And but yes, to answer your question, most of, in fact, all of the environmental analysis that we do is done in-house. Now, some bits of it, yes, every project brings a new constraint. Sometimes it's the geology that's the constraint. Sometimes it's the climate. Sometimes it's the terrain. Sometimes it's and every time we see this challenge, we see an opportunity. I think the time we get really stuck is when someone gives us a really nice, clean piece of land in a nice, landscape setting, and we really don't know what to do with it, and they want to build a little house, which is, and we don't really know what the issue at hand is. So that's one piece. The second piece is that all our projects go through post-occupancy evaluation. So we have on completion 1 year, 5 year, 10 year. And the POC that and of course we get the data from whoever gives it every year in terms of their energy bills and all of that. But our post-occupancy that we do is based on going back to the project and interviewing the users. Mm. And we find strange things that we didn't design for are being used in certain ways because they really like that. Yeah. And some things that we designed for may be performing okay, but is not what the users want in a building. And we sort of have a feedback loop that then goes back, and we sort of have this knowledge management structure where what worked best, what didn't work, and we come back and we refine our models. But it's all done in-house. It's done by the architects of the firm, and that's it.
Yeah, good. Thank you. I mean, let me ask the audience here. We've got some 60 people who who are attending this session. Are there any questions or comments that you wish to direct toward Manit? Any of our Indian students?
There's a question on the chat.
Yeah. Miguel Fancy. Oops, where is it? Thanks a lot for the exciting presentation. I wonder, how do you address two crucial issues in most constructions? One, the sand used in the concrete mix, and two, the land excavated to create what you call the underbelly of buildings. Manit?
Sure. So if you notice, not all our projects have underbellies, and the underbellies come in projects where the soil bearing capacity is at a point where the foundations had to go down by at least 3 to 4 meters to achieve the SBC of the at that point. Now, when you're dropping down, so you have two options: either you pile or you excavate. Now, when you excavate, you get a natural underbelly. So rather than excavate, take the foundations down, put the soil back, and then put the building. We just take the soil away and use that earth. So first and foremost, the topsoil is very precious. It takes 100 years to make topsoil. So that is all saved. The rest of it is used, and the rest of it is used in site fills. It's used in part of the concrete, etc. But we don't do that everywhere. If you have a high rock strata, we wouldn't do an underbelly. We'll find some other strategy. It goes to the geology of the land. If I black cotton soil somewhere, I know I have to remove it to get to Mother Earth or to get to Mother Rock, if I may, and that's how you get the underbelly. So it's not a design decision abstract of the soil conditions of where the site is.
Okay, thank you. Any others? Okay, Joanna.
Hi, Simons.
Okay, you can speak. Okay, good. Please go ahead.
Thank you.
Yeah.
Thank you for your presentation, Manit. Is very overwhelming, as it was mentioned before. Very exciting. I have a question for you, which is slightly different from the actual building design. You probably have quite special clients that come to you already knowing what your practice can do in terms of environmental design. I also come from a country of emerging economy, and I know how difficult it is to actually implement this environmental design, even nowadays with all the tools, all the numbers we can provide. So my question is, how is your relationship with clients, and how do they come to you? Do they come with just a conventional brief, and through your knowledge and your experience, you convince them of the advantages of doing environmental design? Do they already come because of your environmental attributes and the image that you created? How is the process between, how do you relate to the market, basically?
Good question, Joanna. It's been a struggle. Okay, let me just say that to start with, but it's lesser of a struggle today. Now, in emerging countries like ours, and I've always said this in my lectures here, is that form follows finance. Okay, because very few people build for the beauty of building. Money, the cost of the project is really, really vital. Now, when you're telling a client, and if you can prove it through metrics and evidence that your building will consume half the energy that you thought it would, your bills to your tenants or yourself will be less than half of what you think. If that comes to you at a cost that is lesser than what you think, then it's a very easy sell. And that's the sell. So you will, so a lot of my talks are about a green building is one that is cheaper to build and cheaper to run. The problem happened in environmental design, and this is what. So the reason I'm a founder member of RIA. So about a decade back, when LEED came to India, and I'm not taking anything away from them, they brought the green rating system, but they would not give a green rating to a naturally ventilated building or a hybrid building. But their argument was that thermal comfort has to be achieved through the, and the definition of thermal comfort was so narrow that you couldn't do it without central air conditioning. So only a central air conditioning building would be green. And then that set the notion that if I'm LEED Platinum, I may be spending 10% more in my cost of construction, but I have a 7-year ROI. And in emerging countries, no one spends a penny more. It's taken me a decade to bust that myth. That's not true. The range of thermal comfort is much wider. It has to be understood in the context of the external environment. So it's sort of breaking that mindset of that sort of hard ideology of modernism of where you're abstract from the climate. But it's taken a long time, and it's much easier now. It's much easier now. But I think, and in that sense, I think when issues like COVID happen and adversity comes along, people become they understand the fact that even if not for money, it's still worth saving resources. But it has to be it can't be the sell of a green building costs you more and a well-designed environment. Well, if it does, then you haven't solved the problem.
Yeah. Thank you very much.
Yeah, thank you, Manit. But having the buildings and having analyzed them after they're occupied and being satisfied that they've done what you wanted them to do, then it becomes very possible to take the client, the prospective client, around with you to see the building, to experience the building. I mean, it makes a huge difference from showing things on paper.
Absolutely.
Even if they believe in science and in the predictive capabilities of, let's say, computer simulation, whatever, then it's not the same, especially with daylighting, especially with the effect, let's say, of a contemporary jolly can make to the light with and without the sun coming in. I mean, one thing to show the, the simulation, and completely another, especially if the climate helps you in the sense that the sun is there every day, and then, compared to, let's say, us here. Now, so someone called Tanshi, I think, started writing a message, but then stopped. Tanshi, are you around, and would you like to raise the question?
I see the message. What is your advice for young architects starting their first or second projects to work as sustainable architects? How do you solve issues with clients wanting a 1,600 to 2,000 square feet residence, generally MIG, to work in the direction of sustainability?
Oh, couldn't be made more specific. Are you answering?
Okay, I'll answer it. Tanshi, let me ask you. So what is the in my local dialect, I would say, "Mudda kya hai?" What is the issue? Okay. What is the problem you're trying to solve? Right? What is the problem of your client? Okay. Now, how do you solve issues with clients wanting a 2,000 square feet residence, generally MIG? Now, a residence, whether it's 1,500, 2,000 square feet, I mean, there are a million ways to go. Number one, the material. Okay, what material you use? Is the material sustainable? Is it from sustainable sources? What is the life cycle of that material? One. Two, in terms of that can you take that 2,000 square feet apartment and say that through the year they will never switch a light on during the day? They will never need an air conditioner. And just with a fan with their windows open, they will be comfortable through the year. Can you design that? And of course, they can go add an air conditioner later. That doesn't matter. But the question really is that, what is the challenge that you're giving yourself? I mean, it has never. We've done an art gallery recently, which is only 400 square feet, and we found sufficient challenges to work with. It's not about size or scale. It's not about. It's really about what Just take that one thing and see if you can, because architecture is about building small wins over a long period of time. It's very rarely about one big win that'll happen and change your career. It's like accumulating very, very small wins and find your win in there, and every project has a possibility, even if it's designing a door, there's a win in that. So find your problem.
Okay, so Manit, yet again, thank you so much for joining us today. My best regards to Sonali and the whole practice of morphogenesis, all 100 and something, I think, of you. And now that I'm trying to say goodbye, there is a message. There is a message from...
Tarang, how has COVID affected design of your ongoing project, and what changes you think will be considered while designing in the near future because of COVID? Okay, I'm going to just give you one quick example because then we are out of time. So there was this really large building that we're doing. In fact, it's the world's largest office building, single office building. It's about 70 lakh square feet. How much is that? It's about 700,000 square meters. Single building. It's about twice the size of the Pentagon. And there is a reason why it's that large. Now, when we designed the vertical transportation system, and there are about 70,000 people who work in this building. So, of course, we had the vertical transportation consultant, VD consultant, we had the security consultants, and we designed this high code, low code lift system. And we had this lobby where, this sort of 40, 50,000 people would come to, go to different lift codes and shoot up. Now in COVID, okay, we've changed that design and the building is already in the construction. Why? We don't want 50,000 people coming to a single lobby. So we've now taken the high codes and low codes to different levels. And we've broken up the 50,000 into 10 and so we've got that. And we've divided the building into 5 different segments of 10 floors each. So now each core only shoots, so it's like 10 different buildings stacked on top of each other. And the whole notion of how people move has completely transformed. And we found that our wait times have actually improved. So there's not anything directly maybe to do with sustainability, but it does. So the fact that we know that in a 20 passenger lift, you can't put more than 6 people anymore because of COVID. What do you do with a building that's got 20,000 people working in it? When they all come back to work. And the other thing that we've begun to do in all our buildings is night purge. Which was, by reversing the AHUs of breaking out. Third thing we're doing, all facades are operable. Fourth thing we're doing, we're getting rid of anything that encapsulates space, whether it's a shaft, a false ceiling, a suspended ceiling, anything. Everything has to be accessible, open. So the impacts are very large and very many. Some we are doing in existing buildings, but the new thought process is very different. I mean, when we're designing now a residential development, we're not designing it as a 3-bedroom apartment or a 2-bedroom apartment. We're designing it as a school in the day because the kids may have to study from home. We're designing it as an office because the husband, the wife, they may be working as a social space, as a recreational space. It's no more one function to one space. It's not a bedroom. Now there are 4 rooms that can do multiple things through the day, through the year. And that changes how you perceive that space, how you analyze that space. So yeah, there are a lot of repercussions, but interesting ones.
Okay, and on this note, thanks again, Manit, and thank you all for joining us this afternoon to this keynote lecture, and bye for now.
Bye, Simos.
Manat.
Bye, Paula.
Bye. Thank you so much.